So we are dealing with the 11th problem in this series, and the 11th problem in this series is problem number 1.88. The problem is stating a device consists of a smooth L-shaped rod located in a horizontal plane and a sleeve A of mass m attached by a weightless spring to a point B. The spring stiffness is equal to K. The whole system rotates with a constant angular velocity omega about a vertical axis passing through the point O. Find the elongation of the spring. How is the result affected by the rotation direction? And this is the diagram which is provided in the problem. So we begin by constructing our own diagram. So this is the necessary diagrammatic representation of the situation which the problem is trying for us to explain, and this is the axis about which it is rotating, and this is L shaped. When I say it is L shaped, so it means that this angle is 90 degree. Now another important aspect which the problem is suggesting is that the whole system rotates with a constant angular speed. So if omega is constant, then we can say that there is no presence of tangential acceleration or alpha. So alpha is 0, and so is the value of tangential acceleration. And now it is also saying that the weight m is attached to a sleeve. So when I say the weight is attached over here, which is making an angle 90 degree, and it is a sort of a rod. So over here we can say that if this system is to be rotated, then it will be provided by a normal reaction force in this direction. There will be two aspects of normal reaction force. So the first thing that we need to understand is that the weight mg of the block is in the downward direction, of the sleeve is in the downward direction, and it is also supported by providing a normal reaction force in the upward direction, which we are mentioning as n naught. And the circular motion which we are discussing is in the horizontal plane. So we can say that the mg force is balanced by the vertical normal reaction force, and while solving this case we can ignore the vertical forces, and we are only going to discuss about the horizontal forces. So in this diagram, the first diagram that we have, so I have identified the vertical forces, and in this side diagram which I have drawn, we are considering the horizontal forces. Now as it rotates with an angular speed omega, this sleeve is going to be acted upon by a force, and over here I consider this one as a z axis, or the distance is equal to r. We are mentioning this distance from the axis of rotation equals r. So this distance is r, and we are considering this angle as theta. So let L be the length of the spring originally, and after a while, as it starts rotating, the length becomes L plus delta L. Now the problem is asking us to evaluate the elongation produced in the spring, but it must also be kept in mind over here one very important thing, that the answer given is elongation per unit length. So we'll come to that when we solve the problem. So these are the things that we need to understand, and over here we construct one more plane like this, and we are naming this as y axis, and this one is named as z axis, where y and z are perpendicular to each other. Now the first thing that we do is we solve for this theta, or we establish a relation between this r and L plus delta L. So over here we can say that cos theta equals base, that is L plus delta L, by hypotenuse, which is r, so by r. So this is the first expression that we write, equation A. Now we think in terms of the forces which will act in the y-axis direction. So if we think in terms of the forces, let us identify the forces. So the first force that we identify is the normal reaction force which will be provided by the sleeve in this direction. This is the vertical component of force which we have already discussed, and this is the horizontal component NR in this direction. The spring is going to exert a force in this direction which we regard as K delta L or Kx, and due to the rotational sense we will have a force m omega square r in this outward direction, which will be directed like this. So we write it as m omega square r in this direction. So we have a z axis and we have a y axis. So for equilibrium we begin this way, that the forces in the y direction is to be equated to 0. So if the forces in the y direction is to be equated to 0, so in the y direction we have a component of normal reaction force. So if this angle is theta, this is 90 minus theta, this is theta. So the first component is nr cos theta, this angle is 90 minus theta. So we can write the component of normal reaction force or n cos theta, and this is going to be balanced by k delta L sin theta. So this is the first force equation that we have in the y direction. And now in the z direction, if we write summation of force in the z direction is equated to 0, so then we say that the forces in the z direction is to be considered. Then we have a component of normal reaction force. So the normal reaction force is nr cos 90 minus theta, this is nr sin theta. We are writing nr as n over here. And the component of spring force k delta L cos theta, and both these forces are equated to m omega square r. Again, it must be kept in mind that there is a absence of tangential component of acceleration, as omega is constant in this problem. So now all we need to do is substitute the values. So the first thing that we do is we put the value of normal reaction force, and the problem is asking us find the elongation of the spring. So we need to solve for delta L. So from equation 1, so we can put the value of normal reaction force as k delta L sin theta by cos theta, and we have one more sin theta plus k delta L cos theta, which is equal to m omega square r, and r can be written in terms of L plus delta L by cos theta. L plus delta L by cos theta, we can write it in this sense. So over here, if we substitute all the values correctly and we solve, so we end up getting the value of delta L. So delta L value turns out to be L upon x by m omega square minus 1. So this is the expression that we get, and it must be kept in mind that the solution or the answer given in the textbook is elongation per unit length. So over here we have calculated the elongation value, which is in terms of L, which is the natural length of the spring. And the question is also asking how is the result affected by the rotation direction. So the elongation is independent of the direction of rotation, as it will not change anything about the force equation which we have. So this is how we solve this problem number 1.88.